Okay, thank you very much. Let's continue with material balance calculations 2. That's module 3.2 is a continuation of module 3.1. We just divided that into 3.1, 3.2, so the video will not be so long. We're going to look at introduction, look at solutions to material balance problem for systems at steady state. We'll look at processes involving chemical reactions, use of tie components, then recycle, bypass, and purge operations, and we'll conclude. Processes involving chemical reactions. With chemical reaction in a process, material balance procedures will change. The stoichiometric equation of the reaction imposes constraints on the relative amounts of reactants and products in the input and output stream. See, now there will be chemical reaction, so stoichiometry of the chemical reaction will come in. Thus, the general material balance for a reactive system at steady state is given as input plus generation equal to output plus consumption. Now, elements are not destroyed in chemical reactions. We write the elemental balance as input of element I equal to output of element I plus accumulation of element I. Remember our law of conservation of matter. And then this equation can be written for inerts, that is inert species. And these are species which do not enter into the chemical reaction. They go in and come out that way. We'll see from the examples. Like insolubles can be considered as inert. Of course, for steady state operations, the accumulation term vanishes. Example, the first example, we want this example to show this. Pure ethane, you see, we are given that question, is bond completely with air to form CO2 and water vapor. For each mole of ethane, 18 moles of air are supplied. Look at that. First thing we do is to sketch the flow chart. Then since the combustion is complete, the chemical equation is written. We're looking at process with chemical reaction. System is the furnace. Then we will choose our basis, 1 mole of ethane. Now since there are 5 species and 1 reaction, we can make 4 independent material balances. Amount of air supplied is 18 moles is given. Therefore, amount of air supplied is 0.21 times 18. Remember, the percentage of oxygen in air is 0.21%. So multiply by the 18 moles will give us the amount of moles of oxygen that is supplied. The amount of nitrogen supplied is 0.79 multiplied by 18. Remember, the percentage of nitrogen again in air gives us that. And nitrogen does not take part in the reaction, hence nitrogen is an inert. So look at what we've done. You just come down and write this down and find out if there's any confusion, then you can ask your question. Use of tie component. A tie component is a material which passes through a process unit unchanged. It doesn't get involved in the reaction. In other words, a tie component can only exist in 2 streams, one input and the other output, because it cannot go into accumulation or generation. It is not part of the reaction. So for instance, in the last example, nitrogen is a tie component since it passes through the process unreacted. Knowledge of the percentage of a tie component in 2 streams establishes the relationship between the weights of the streams, so that if one is known, the other can be calculated. Now, in combustion problems and in some more complicated types of industrial chemical calculations, the use of tie component greatly simplifies the calculation. So we can use tie components. In general, however, one should not use as tie components species which are present in very small quantities, trace quantities. So we say trace components may not be accurately analyzed. This is why we can use trace components as tie components. Example 2, you see the problem there. We've tried to solve it step by step. So take your time, look at it. The first thing is to draw the flow chart. What system are you looking at? What is your basis? And then you start making your calculations from there. Now, when we have recycle, bypass, or purge, if you see the diagram there, because many industrial processes operate recycle streams. So look at the diagram there, you see recycle. It's coming from separator. It has been recycled back to where the fresh feed is coming. So which means certain percentage will be fresh feed and another percentage will be recycled feed. So what is entering now is not fresh feed alone, it is fresh feed with recycled feed. So the feed to the process itself is made up of two streams, the fresh feed and the recycled material. If some of the stream variables are unknown, one can calculate these by writing material balance about the different streams. Another operation that is similar to recycle is bypass, where a fraction of the feed to the process unit is diverted around the unit and combined with output stream from the unit. So we can also have bypass, split the process feed, bypass a certain quantity without allowing that quantity to go into reaction. Thus, by varying the fraction of feed which is bypassed, the composition and properties of the product can be calculated. Now, one problem that is usually encountered with recycling operation is the gradual accumulation of inert. Remember, we said that inert does not take part in the reaction. So while you are recycling, you are now bringing the inert back to the feed. Now, the inert will be adding to the inert in the fresh feed, and then you have a kind of accumulation of the inert in that recycle that is also meeting the fresh feed. But this problem can be solved by bleeding off a fraction of the recycle stream. And this bleeding off is what we call to purge the system or purge operation. Look at another example, a lengthy one, complicated, but we took it step by step. First thing you must always do is to draw the flow chart. Because if the flow chart is not correct, then whatever you're solving is likely to be wrong. So if you look at this, we now have recycle of hydrogen, passes through the reactor, goes through the condenser, then there's a recycled fraction, which means the fresh hydrogen feed, and then goes into the reaction. So take your time, look at the solutions to the problems, what we solved, and if there's anywhere there's any confusion, you ask your question in the group chat. That's still that same problem, and at the end we now have all our composition of the product stream. Thank you very much. We're done with material balance calculations under steady states, process with chemical reaction, recycle, bypass, and purge operations, and of course some examples. This time I think there are many of them, about 3 of them for us to understand. So we will be proceeding to the last module for the course, that is module 4, which has also been divided into 4.1 and 4.2. So I hope you enjoy this class. Expecting to see you in the next class. Thank you very much.